offer at GuardSquare. So mobile threats can be divided in 2 to 3 categories. The first one is the static analysis. So there, a malicious user is going to decompile your mobile application on his own machine. He can use various tools for that. He can take a look at the source code, try to understand what your app is doing, but he can also try to change a certain behavior statically, repatch the app, and use it on his own device or distribute it as a clone. A second attack is a network attack. This can also be considered as part of dynamic analysis. And during a network attack, people can perform a so-called man-in-the-middle attack on the app. It can be on its own test device, but it can also be done on a real user's device to target that specific user. Once the man-in-the-middle attack is performed, the attacker has the opportunity to take a look at the network traffic that's sent. And by doing that, he might sniff the end user's credentials, or if he performs this attack on his own device, he can, of course, get a better understanding on how the API works and how the app communicates with the backend. On dynamic analysis, the attacker is going to run the app on his own device. This gives a couple of advantages. For example, he might be able to attach debuggers or hook the app with tools like Frida, Exposed, or any tool that's capable of doing that. And he might try to change the behavior of the app dynamically. Some examples are, for example, he might try to hook a license check in order to make it return that the license is always valid, even if it's not. He can also dynamically try to patch out certain checks, for example, to see if a device is rooted or jailbroken. So these threats can be coming from all different perspectives. So of course there might be malware installed on the device that's targeting your application, but also keyloggers or spyware overlay attacks might be there, and they might try to sniff your users' credentials or any other information that they enter in the device or enter in your app. Also, of course, people can use decompilers or other reverse engineering tools in order to disassemble your app and get at least an understanding on what it's doing on the back end and maybe change certain stuff. So the things you really wish to protect, of course, are the intellectual property. It takes a lot of effort to develop an app, and it's not really nice if somebody would somehow steal all the effort that you did and copy your work and reuse it in his own projects. Also keys, for example, cryptographic keys, passwords for databases, API keys, and so on, can also be something a malicious user wishes to steal. The next important part to harden is the authentication mechanisms, if it's applicable, of course, as well as the secure communication between the app and the backend. Also, the advertisements is important to protect. I see a question coming in. So how many frameworks do you support or stop? So at GuardSquare, we actually detect the traces these tools leave behind. So it's difficult to put a number on that because we will recognize these traces, and therefore even private frameworks that we are not yet aware of can actually also be detected by our tools. But we tested with Frida, Exposed, Substrate, and I believe a couple of others which I do not immediately recall on top of my head. So the advertisements is of course also an important part to protect. Think about the Janus vulnerability in Android, where it was possible to change the advertisements in such a way that the revenue from these advertisements was going to the attacker instead of to the developers of the application. If you display ads to your users, you of course want to get the revenue from that and not somebody else. So some examples for tools that allow static analysis, and I would really recommend everybody here to check out these tools later on and try to use these on your own project to see what's visible in your app or in your SDK, and see if that's really desired, that this is visible. So some ideas, for example, are IDA Pro, Hopper. These are commercial tools, but also open source tools are available. Think about APK tool, DexDump, Paxmali, Jet, Dextujar, and so on. For Android apps, it's really simple. You can just drag and drop your Android app to Android Studio, and it will decompile that. Behind the scenes, it will make use of APK tool and Paxmali, if I recall correctly. So this is an example on where we applied a static analysis on an open source project. So as you can see, all the classes as well as package names are visible here in plain text. They have not been obfuscated. It's easy to understand what these parts are doing. A special class, the proxy card class here, might attract, for example, the attention of a reverse engineer or a malicious user, especially the methods like get CVN, get expiration month, get expiration year. With obfuscation, you would be able, of course, to rename these to random names that at least the context and the meaning of these methods are gone. But it's also possible, of course, to apply more advanced techniques of obfuscation to, for example, mix the control flow inside these methods. For dynamic attacks, there are also, again, commercial tools as well as open source tools available. You can use the fault debuggers that are shipped with Android to analyze your own app. Frida is an open source tool. Exposed is also a tool you can use to hook certain things. And for network analysis, I would recommend to check out Wireshark or the Burp Suite. Here we see an example for, in this case, iOS, but of course, doing something similar on Android would also be very possible, of course. So this is a Frida script where we hooked the isPremium instance method of the class user. In this case, we are going to make sure with Frida that the instance method isPremium will always return true, and therefore we actually cracked all the premium features inside this app without having to pay for it. So let's dive into some case studies on what would be interesting for reverse engineering or for reverse engineers or malicious users to do. So, for example, API key extraction. In that case, of course, it's necessary to first download the app from the Play Store, or in case of iOS from the App Store, and then get a decrypted version with Frida. Once the decrypted version is available, or the APK for Android, we can use tools like strings or Android Studio to search for security-sensitive strings in there, which might be API keys. These API keys can then be copied, and for certain services, as you all probably know, it's necessary to pay for these. So the attacker can, in this case, reuse that API key and get actually access for free to that server. And if you have to pay for it for every request, for example, your company will get charged for the attacker's usage of that API key. It's also possible. I see another question. Okay, I will take a little break after every slide. So if there are any questions, please do not hesitate to ask them in the chat. How do you protect the API keys? Well, that's a very good question. We give you the opportunity to encrypt strings inside these binaries or resources. So they will be encrypted during the build or processing time of your app. Once they are encrypted, they are hidden from static analysis. Of course, at a certain point in time, your app will need that API key to communicate to that service. And therefore, we will insert decryption algorithms together with the encrypted version of that string, so that your app is able to decrypt the strings at runtime. Of course, you could argue that you can read these out of the memory with a debugger or by hooking again, and that's very true. And that's why we actually use a multi-layered approach. So there will be other features available on anti-debugger features and as well as anti-hooking features, which then protect against that kind of attack. The more features you will add to the app, or the more layers of protection you will add to the app, the more difficult it gets for reverse engineers to get their hands on those keys in this scenario. So how the question is how to protect the key that you use to encrypt and decrypt the API key. So it will be weaved as a kind of an algorithm around the parts where it's needed. So it's not really an obvious key that's located there. That wouldn't be a really smart thing to do. But it stays app hardening, of course. So yes, in the end, it will be possible to somehow extract that algorithm from the app. That will be very difficult to do, but it is possible. And then start to decrypt a certain string in there. The idea is that we raise the bar for attackers, and we raise it a lot so that it becomes way more difficult to get their hands on, in this case, the API key. Will using Android key stores to store keys be helpful? That's definitely a good way to do so, but be careful. It's not a foolproof way either, because, for example, if somebody would root his device, he can gain access to the Android key store. Is there any capability in DexGuard to obfuscate the library code inside a project in case I have included any library inside my Android/iOS project? Yes. If you use libraries in your app, we will process these as well. You can add any protection mechanisms that we offer to the libraries or frameworks too. That's possible. It's important to mention that the library needs to be presented at build time. So if you would somehow dynamically download it from the internet when the app is running on the device, then of course we cannot protect it. Moving forward, so it's also possible, for example, to insert malware inside your application. So in that case, the attacker will need to download the app again first. He can then insert malware and distribute your app as a clone. In this scenario, the attacker inserted code to perform a DDoS attack, and the user's devices will actually participate in this kind of attack without them knowing. See another question coming in. Is the string constant obfuscated? Can you please elaborate a little on what string constant you are referring to?
Pooja, you can talk, you can unmute and talk. It's okay.
The string constant that we define in the project for some keys and constant variables that we define throughout the project.
Yes, that's of course possible. You can encrypt these as well.
Yeah, because using ProGuard, the string constants are not easily obfuscated. So.
That's indeed a good remark. ProGuard is our open source tool to actually optimize Java code. Yeah. So we don't really advertise it as a security tool. So all the security tools are part of the commercial tool DexGuard. But ProGuard gives already a good look and feel on how DexGuard would be integrated and configured in the project. Also, all the key rules that you have in place for ProGuard, DexGuard will understand these as well, so it's backwards compatible.
Okay, thank you.
So a malicious user can also be interested in harvesting credentials from users. For example, if you have a video streaming service, it would be really nice for the attacker if he could clone the app and change the app in such a way that when a user would log into the video streaming service, that his credentials will actually be sent to the attacker instead of logging in like it would normally do. Of course, you will need to distribute a clone for that. And if the legitimate user is tricked into believing that that is the real app, then he might actually enter his credentials in there. The attacker gains access to these credentials and can then use that service for free, or even worse, distribute it to other people in order to be able to make free use of your service. I see another question coming in. We did ProGuard of our SDK, but our customer in his enterprise app using SDK as library trying to use DexGuard. Are ProGuard and DexGuard both incompatible? Indeed, these are incompatible to use together. So if you would like to use DexGuard, then you need to disable ProGuard. It will throw an error if you don't do that. But of course, DexGuard has all the functionalities that ProGuard has, and it will add, of course, also more functionalities on top of ProGuard. If you have a certain SDK that is already obfuscated by ProGuard or any other obfuscator that is available, both commercial or open source, it's a best practice to blacklist that SDK for obfuscation, as obfuscating something twice might result in really difficult bugs to debug, or it can bloat the application, meaning that it will increase dramatically in size. So of course, the previous use cases. Sorry?
Yeah, I have one question. So how will be the attacker will be able to clone an app and redistribute in Play Store? When the certificate is being saved, you should not be able to clone the app, right?
So do I understand you correctly if I say that your question is how the attacker would clone an app, like practically?
Yeah, even if it clones, you will not be able to redistribute, right? Because authority of the app is not compromised. No?
Well, the attacker,
please.
The attacker, of course, needs to resign the app if he wishes to redistribute it. And if it's through the Google Play Store, that will indeed a little bit more tricky to do, because you would need to change the app package name, for example, as well. But it is possible. Also for Android, there are a lot of different distribution channels which the attacker might use to distribute his app to other unknown users. The resigning of an app is something that DexGuard and IXGuard will also detect, because that's, of course, a good indication that something is going wrong. I see another question. If we use native code, C++ as GNI and .so, do I guess we may not need ProGuard? Well, ProGuard, as far as I know, will indeed not process the native code. DexGuard, however, can. So also in native code, if you develop it with C++, there will be some things that might be interesting for an attacker. These shared libraries can also be decompiled using different tools. You can take a look at the assembly code in that case, or security sensitive strings that are part of that library. DexGuard by default, without any add-ons, will be able to encrypt your .so, that's part of your app or your SDK, and it's more like it would encrypt the entire file. If you want to apply additional protection, that's possible with the NDK add-on, and in that case, DexGuard is also capable of encrypting security-sensitive strings, obfuscating the control flow, as well as arithmetic operations inside the actual C++ code. So the previous case studies were, of course, just drawings and examples, but these kind of things happen to real life apps as well. So what you can see here is an example of iOS photo vaults and Keepsafe. This is all public information. So if you're going to Google these names, you'll normally come across the article which described in detail how they disassembled the app and what they changed to, in this case, get access to the protected images and pictures behind these apps without knowing the passcode. So how did they do that? In a nutshell, they of course first needed to statically analyze the app to get a better understanding on how everything was working. They then hooked that lock screen. They verified if they were at the right view by hiding one of these boxes that, well, you can see here, there are 3 boxes displayed, but originally there were 4. So that confirmed for them we're in the right view, and then they could actually simply just call the method dismiss lock screen, which would have been called if a correct passcode would be entered, and the lock screen just disappeared, and they had access to all the images and pictures that were in that safe. Using a jailbroken iPhone, it was also possible to navigate through these apps files, and the password was actually stored there in a really insecure way, and they could just read it in plain text and also, well, enter the passcode or change the passcode to that app. So what went wrong here? I see another question coming in. Is it possible to bypass login/pin screens in Android also? Yes, it depends on how it's written. If it would be written in a bad way and not protected against reverse engineering, just as it was in this example, then that would be possible on Android too. So the vulnerabilities for both iOS and Android are really similar. Their philosophy is actually the same, but of course different tools and different techniques need to be used to achieve the same goals in both Android and iOS, since the operating systems are entirely different. But in the end, the results can be achieved in both operating systems. So what went wrong in this particular example? Well, first of all, there was no really strong protection against static analysis, making it more easy and faster to know where and what they needed to hook in order to bypass this login screen. Also, no protection against hooking or swizzling. As you probably already know, swizzling is just another technique to change the implementation of a certain method. So there was no protection applied against that, making it possible to call that method using the script. And of course, then there was also the insecure storage. So instead of using the keychain, they just stored it as plain text in the file, which is also a really bad thing to do. So to summarize, there was no multi-layered protection. Another question, but iOS is more secure. What features TextGuard covers to protect any iOS apps? That's actually a common misconception to consider iOS more secure. It's true that Apple puts a lot of restrictions and efforts in security towards their end users, so towards the users of, for example, an iPhone or an iPad, but they actually offer very little protection for developers. So for the developers, they have the Fair Play DRM in place that encrypts your app. But if you run the app on a jailbroken device, it's actually very easy to get a decrypted version of that app using a tool like Frida or Cracker, for example, and you will get access to the IPA nevertheless. So what features do we offer to protect iOS apps? Well, it's actually very similar to Android. Only, again, other techniques are used. So we offer you name obfuscation, together with more complex forms of obfuscation. Think about control flow and arithmetic obfuscation to shuffle the control flow in a random way, or replace simple arithmetic instructions with more difficult ones. And on top of that, we also provide a RASP feature set. So we're able to detect jailbroken devices, debuggers. We can detect if the app is hooked or, for example, resigned, if any dilibs are inserted, and so on. And if a threat against that is detected by Xguard, by default, your application will crash, but you can disable the crash if that's unwanted behavior and use a callback instead, for example, to notify your backend for that particular user. So let's take a look at maybe a better known example, and in this case, an example for Android, Pokémon GO. So a common way people cheat in Pokémon GO is by spoofing their GPS location. So they have some kind of joystick printed on the screen on top of Pokémon GO, and using that joystick, they can actually move around the map instead of from their coach, instead of well, actually walking outside and going to these locations. So that was one thing they wishes to avoid, of course. They don't want cheaters to use their app. And they try to avoid that by detecting if a device was rooted. And that's indeed a good first thing to do, but it's, well, it's not sufficient to fully harden against this kind of cheating. And actually, the root check wasn't really well implemented because it can be easily bypassed using, for example, root cloak, risk hide, or any other root hiding technique that was available. So what went wrong here? Well, they had a root detection, but they didn't have any root hiding detection techniques in place. So with root cloak, you could easily hide that the device was rooted. And of course, as these root hiding detection techniques rely heavily on hooking, they also didn't implement any protection against hooking itself to prevent this kind of attack. So in the end, again, you could say that no multi-layered protection was applied, and therefore it was quite easy to bypass it. Another example for Android is the 7Pay app. The app fell victim for an attack where there was unauthorized access to users' accounts. It was a payment app, and the users lost a lot of money in total. It's at the moment not really clear what exactly happened, what happened here, or how the attack was performed, but some possible scenarios might be the following. Somebody could have probably cloned the app, distributed through different channels, and some users might have believed that it was the real app, entered their credentials, and their credentials therefore got stolen. It's also possible people will use the man-in-the-middle attack in order to sniff the network details that were passed to the backend servers, and stole the user's credentials that way. But it can also be that malware was installed on the device, and for example, using an overlay attack, the passwords as well as the usernames or email addresses used to log into this app got stolen using that overlay attack. So what could go wrong in such a scenario? Well, there was no tampering detection. Tampering detection could have prevented people from distributing these clones, as you can make the application crash if you detect that the app is resigned, for example, or changed in another way. Also, it can be possible that no communication hardening was done, so no SSL pinning, no hardening of that SSL pinning implementation, and therefore making it possible to perform a man-in-the-middle attack. It might also happen that there was no protection against overlays or keyloggers, making it possible for malware to sniff the user's credentials using an overlay attack. So again, we can summarize this as there was no multi-layered protection added towards reverse engineering for this application. So another well-known example, WhatsApp. It's actually they fell victim on both Android and iOS, and they fell victim for commercial spyware that was inserted in their app, and that way actually the attacker gained access to the data that's recorded by the microphone, camera, even messages on the phone, as well as emails and location about users, or data about users' location was stolen from WhatsApp users this way. So what went wrong here? Well, first of all, there was no tampering detection, making it possible to statically insert this kind of spyware. And of course, also no code integrity protection was done in WhatsApp, making it possible for malware to change it dynamically, for example, in order to insert code that actually shouldn't be executed. So again, it can be easily summarized in one sentence: no multi-layer protection was applied to this application. Which algorithms does DexGuard use internally for encryption? Well, of course, I cannot. I'm actually not aware of the exact implementations, and if I was, I couldn't disclose it, unfortunately. But what I can tell is that DexGuard actually has a pool available of multiple different algorithms. So both DexGuard and IXGuard actually will randomly select encryption algorithms for classes, strings, resources that you wish to encrypt during the build time. And by doing that, we actually make it more difficult. So let's say an attacker is somehow able to encrypt one of the strings that you have encrypted in your app, then he's most certainly not going to be able to use that same technique to decrypt another string, because that other string is encrypted with a different random algorithm. So that changes every time you build the application as well. Making it more difficult to analyze what the app is doing, or breaking the obfuscation of the app across many updates that you have published for your application. Cool, sounds interesting, thank you. So one way to protect against this is, for example, what Pokémon GO could have done. So they might have searched the web for some algorithms to check to verify if a certain device is rooted, and you can do that too. You can go on the web, and there will be a lot of scripts available that you can just copy paste to see if your device is rooted or jailbroken, or if a debugger is attached, and so on. However, as these next slides will indicate, that's probably not the best thing to do. So let's take a look on what's wrong with that approach. So once you would start searching the web, for example, to see how you can detect if a certain device is jailbroken, you will definitely find back this really simple algorithm. This will actually try to open a terminal with root access, and if that works, then you know the iOS device is jailbroken, and you can implement your custom response towards this threat. So what's wrong with it? It's actually too basic. It's a really well-known check, both for developers, but also for attackers, and attackers already know how they can bypass it. Also, in this scenario, it would only be executed once. So in contrast to the ones we insert for you with IXGuard, we insert it on many different places, and you can set a variable on how aggressively these checks need to be inserted. So in fact, how many of these checks need to be inserted. And if you only call it once, well, it's actually easy to bypass it by patching it out statically. You could, for example, change the 1 to a 0 to give one example. It always looks the same, so yeah, it's a known check, and it's also not inlined. On the right-hand side, you could see how this check can be bypassed using a hooking technique. So you could hook the system method here and just making it always return 0, even if the device is jailbroken, and therefore this detection technique would be bypassed. So you could do something very similar for Android as well. You can open this. You can search the system path and see if SU is mentioned in there somewhere. If that's true, then that can be an indication that indeed the device is rooted. However, just as with the previous check, this is actually way too basic to do it. Also, it would be necessary to check for this more than one time. And it's a really well-known check, both towards developers as well as attackers, so they already know how they can bypass this. And that's actually shown again on the right-hand side of this slide. So this is a snippet that's coming from root cloak, I believe, which is a tool you can use to hide that your device is rooted. And what it actually does is it's going to see for itself if these strings are available in the path, and if so, they will remove these from that string that's passed to your detection technique, and therefore you cannot see anymore if SU is presented in these strings or not. So again, with hooking, this can be easily bypassed, and it's actually already available as an open source tool in root cloak. In a very similar way, you can search the web to see if you find any debugger detection algorithms. And one you might come across against is the one you can see here on the left-hand side. So this technique will deny the attaching of the ptrace debugger. However, by hooking DLSIM, it will again be very straightforward, as you can see on the right-hand side of this slide, to pass a fake ptrace and make sure that you're actually still able to debug this application. So very similar to the jailbreak detection checks we had in place. The things that's wrong here is it's too basic. It's only one check that's also only called once instead of spreading it across the application in multiple different locations, and it's not inlined. So you could actually also just hook the method protect here. In a very similar way, you can also detect debuggers on Android using a technique Google made available in the Android SDK. So you can call debug.isDebuggerConnected, and it will return you a Boolean value to see if the app is debuggable or if a debugger is attached to the app. But again, it's really easy to just hook the isDebuggerConnected implementation and changing it in that way that it will always return false, thus making your detection technique believe that no debugger is attached even though there is. So again, as with the other techniques, it's way too basic. it's not inlined. It looks well really similar, so it looks always the same. And as this is a common technique to detect debuggers, both the developers but also the attackers are already aware of this technique. What preventive measures are taken by GuardSquare to avoid bypass of jailbreak or root device condition? So that's where, again, the multi-layered approach comes in handy. So well, what we do different for just jailbreak detection, for example, is we have a lot of different checks, which we will again select randomly from a pool during the processing time, and these will get inserted randomly through your application. So it won't be a check that's inserted only once, it's inserted many times, up to 40, 60, 100. It's kind of configurable to a certain extent. And the amount of combinations that we can use to check for jailbroken devices is about 400. So it would require a lot of effort to hook all of these checks and all of these different combination of checks for a malicious user. It's not impossible, of course, but then the hooking technique will, or the hooking detection techniques will detect that you're using a hooking technique to patch these checks out, and it will still make the application crash because it's hooked. Also, if you try to do it statically in the bytecode, then the tampering detection will detect that the app is resigned and also make the application crash, and therefore preventing users from doing that. A similar explanation, of course, or it works in a really similar way for Android as well. So as a last part of the presentation, I would like to give you an overview on the solutions that we offer at GuardSquare to harden your Android and iOS apps. So there is, of course, DexGuard, which is the commercial tool or the next tool for ProGuard. So where ProGuard or open source Java optimizer is just an optimizer, although it can apply basic name obfuscation, DexGuard is more of the security tool. So it has way more advanced techniques to obfuscate your code or encrypt certain parts in your code. It's also shipped with a RASP feature set to detect rooted devices, root hiding techniques. It can detect if your app has been tampered with or hooked and so on. DexGuard also offers you the possibility to implement SSL pinning, so in order to harden the communication between your app and your backend. And on top of that, we, just as with ProGuard, actually apply a shrinking and optimization step. The difference in these two steps with ProGuard is that DexGuard will also process your resources and assets, and it will apply more advanced techniques of optimization. So in the end, you will still see an improved results towards the speed and the size of the app. So some of these techniques, especially encryption or code obfuscation, like control flow obfuscation and arithmetic obfuscation, can have an impact on the app in both speed and size. However, thanks to the shrinking and optimization step, DexGuard will actually be able to decrease the net size of your app by 5 to 70% and increase the speed by 10 to 20%. Of course, it's important to only apply these additional hardening techniques to the security sensitive parts of your application, because if not, you will experience an overhead there. DexGuard integrates in the build process as a Gradle plugin. So that's in a very similar way as ProGuard integrates in your project. It's backwards compatible with ProGuard, meaning that all the keep rules you already have in place will keep working in DexGuard as well. it will be necessary to do some additional configuration, as there are more features to configure, of course. DexGuard is compatible with Java, Kotlin. It can obfuscate C++ together with the NDK add-on. And it can also obfuscate JavaScript as part of hybrid apps or C# if it's a Unity game. I see a question, what's the impact on the size of the app? So the size of the app, the net size in the end will actually decrease by 5 to 70%. So your app will get smaller because we can optimize and shrink more than the overhead of the obfuscation features imply. And the integration effort you will need if you're totally new to the concepts and if you have no experience with ProGuard, we tend to say that integrating DexGuard will take about 2 to 3 weeks. If you're already experienced with ProGuard, that's a very good start, and then it will probably take less than 2 to 3 weeks. For iOS, we have a tool called IXGuard in place. The philosophy of IXGuard is very similar to DexGuard, so both tools protect against the same threats, but of course, since the operating systems iOS and Android are entirely different, other techniques need to be applied. So IXGuard can apply obfuscation to prevent static analysis. It can obfuscate the control flow and arithmetic operations as well. It will also apply name obfuscation to the class names, method names, variable names, and so on. It can encrypt security-sensitive strings in your app, and on top of that, it will also give a RASP feature set available to you. So you will be able to detect jailbroken devices, debuggers, hooking frameworks, or you will also be able to detect if your app has been tampered with. So the supported platforms are, of course, the native languages. So that would be Objective-C as well as Swift. But we also support hybrid apps, more specifically Cordova, Ionic, and React Native. And we can obfuscate the JavaScript for these cross-platforms as well. Also worth mentioning is that IXGuard can also protect your iOS Unity game. So the integration is not in the build process with IXGuard. It comes at the end of the build process. It's a command line tool that takes your framework, dialib, or IPA as an input together with a configuration file, and it will then produce the protected app as an output. Something you need to keep in mind is in order to use IXGuard, you will need to make use of Xcode 10 or later, and bitcode is required to enable it for your own source code as well as all the libraries that you use. The performance, there is no performance overhead, also no improvement because the C-line compiler is already very efficient. There's not a lot we can optimize or shrink with IXGuard. Also, SSL pinning is a feature we do not offer since Apple already provides this to you. We will further harden the implementation of Apple, of course. And again, just as with DexGuard, the integration effort is about 2 to 3 weeks for inexperienced users. For cross-platform apps like React Native or Ionic, do we need to integrate it separately for Android and iOS, or can we integrate it directly? Unfortunately, it will be necessary to integrate it one for iOS and once for Android, so twice in total. Out of DexGuard and IXGuard, which one works better with React Native? Both will work equally well, but you will need both if you have an Android and an iOS app. IXGuard will protect the iOS app, DexGuard will protect the Android app. So you will need both tools in the end to protect everything. The feature set that is available is, of course, very similar on both platforms. Last but not least, there is also a tool Threatcast we have available. With Threatcast is actually a monitoring system that will report back to you how many threats have occurred on your app and where they are coming from. So, for example, you can see how many times your app has been hooked in a certain country. You can also see the daily active users for both Android and iOS. And this gives really nice inside information on why it's important to protect that application, of course. Threatcast is a tool that can only be used together with DexGuard or IXGuard. The integration is extremely easy. You just generate an API key in our cloud platform. You copy that API key in your configuration for DexGuard and or IXGuard, and from there on, DexGuard and IXGuard will know what to do with that API key. They will insert all the necessary API calls for you, and you can make use of Threatcast. So Threatcast supports both Android and iOS. It's of course necessary to implement the REST feature set for this, and it will report the threats back to the online platform where you can read that data. So the integration effort and platform considerations are actually none. It's really straightforward, easy, and fast to integrate in your project. So since you collect threat data, do you store any important data with you? So if you choose to use Threatcast, then indeed we do collect data. This data is completely anonymous though, so we do not know what user has rooted his device and run your app. That's also something we do not save or keep track of, so everything stays anonymous. And at the moment, we hire servers with Google to store the data with. So it's not really user-specific information that we have, only information about the date and time when the threat occurred, together with some information of the device that's used. So we know the operating system, of course, together with the brand of the phone, as well as the type of phone that's used and the country that the threat has occurred in, but not like the front door address of that person, of course. Is DexGuard supported for Flutter application development? No, unfortunately, Flutter is something we're not compatible with. For cross-platform apps like Ionic or React Native, is the integration similar to ProGuard, or will it be different? The integration is actually very similar to ProGuard. Threatcast can be integrated with existing admin portal with a widget, or is any SSO available? So Threatcast is a tool on itself. For now, it cannot be integrated with any other tools besides DexGuard and IXGuard or any other reporting tools. There is a premium feature available to export the data in CSV, for example, to further analyze it in Excel or other tools that are compatible with that format. But it's something we might take into consideration. It's a really new tool, so it will get further developed, of course, in these kind of things. Is data from the device to Threatcast platform encrypted while passed over the network? Yes, it's of course protected. Do you have an API which can use for SIEM solutions and show the data? No, at the moment we do not, but you can use the callbacks, for example, once these threats are created, to implement something like that yourself. So you can report it back using DexGuard or IXGuard to that system, but it needs to be implemented by your development team. So this is the end of the presentation. I see there is still a little time left. So if anybody has any further questions, feel free to ask them.
So I think there are no further questions. I thank all for joining this call, and we'll be sending the recording of this webinar to all of you. And if you want to distribute in your teams, or if you want to send somebody, or you want to refer it to your friends, please do so. We are here to answer any queries, and if you want to talk one-to-one, very specific to your requirement, your application, we can schedule a separate call with you, and we can then take it forward. So thank you so much, Vincent. It was really nice and very interesting, and we learned a lot. We'll keep asking you for doing some more things, because we had around 96 registration, only 52 people could join. So we may schedule one more webinar soon, so we can cover the rest of the people as well.
Thank you. We learned a lot.
Thank you. Thank you, guys. We'll be in touch with some more information and some more documents about DashGuard and iTechGuard. Thank you. Thank you, Jess. Thank you, Jonas.
Thank you all for joining.
Yeah, Christina. Thank you so much.